Okay, we'll start the class. The last week's midterm one have been graded, and here is the distribution. The medium score is 13.5 as shown here. You'll learn your own score pretty soon, probably hopefully today. Okay. Just a couple words about the exam. Okay. I would ask students to use the parameter that's listed in this book. Okay. In particular, the intrinsic concentration, carrier concentration is 1 times 10 to the 10. Some of you used 1.5. That's apparent 1.5 times 10 to the 10. That's from some other book. Okay, and that leads to some unnecessary effort in grading. Okay? So from now on, just stick to the parameter of this book, and not from other books. And the other value is KD over Q, that's listed here, is 0.0259, because it's usually the exponential in the exponent. So a little bit off will make a pretty big difference. Okay? So those are my advice for the future exams. All right, so let's go on with this week's questions. 6 questions listed here. So we'll go over them one by one. The first question is talking about the saturation, velocity saturation in MOSFET, and okay, what's the effect on IDS and IDSET? Those are listed here in this chart. Okay, based on the n=1 model, you can calculate the IDSET for any given L, okay, using this equation. And also, and this equation, as we went over in the class last Monday, there are two limits. Okay, long channel limit is the 1 over L dependence. We covered in chapter 5 for the IDSET. But in the other limit, the IDSET becomes independent of L. Okay, so but of course we are not always all the way here. So when you shorten the L, the IDSET can still go up. It's just not as much as 1 over L, like in the long channel case. The key parameter is this dimensionless parameter. Okay, if this parameter, you can see that if it's much less, let's see, for a long channel, this factor is much less than 1. You get this IDSET goes as 1 over L. Okay, same as chapter 5, long channel. In the other limit, when this dimensionless factor is much larger than 1, then it becomes L independent. Okay, so the actual situation is in between. It's not as strong as 1 over L, but it's not constant either. It just can still improve. Also, I would like to point out that often not paying attention to is the Vg minus Vt. So the Vg minus Vt plays a role also. The MOSFET is more velocity saturated at high Vg minus Vt. Okay. So if Vg minus Vt is low, we call it low overdrive, then actually the velocity saturation is weak. Okay, because when this is small, it's more like this factor is much less than 1. In that case, it's like a long channel, so the current is still proportional to 1 over L. And this we'll point out when we go to chapter 8, because when you switch a MOSFET, it's not just the ID set. It goes through different values of VG minus VT. And so when VG is not too far above VT, actually the mobility is still important, and its channel length is still important. Only when VG minus VT is high and L is short, then ID set becomes less dependent on the channel length. Okay. So in chapter 8, we'll discuss how the switching delay changes as a function of channel length. It still depends on the channel length. The other factor, which is not covered here, is the capacitance. Okay? As I mentioned at the end of chapter 5, the capacitance of a short channel device is less than the capacitance of a long channel device. So when we talk about switching delay, it's not just current, but also capacitance. So when you have a shorter channel device, even if the current doesn't improve as much as long channel, but capacitance will improve. So that's why the delay dependence on channel length is more than the current. And that's all discussed to be discussed in chapter 8. Yeah. Okay, next question is as shown here. When channel is short, the gate cannot fully control this barrier. Okay, and that's all described here. Okay, so in this chart, this shows that in a short channel device or channel length of L, the psi 2 is the potential in silicon. Okay, let's say at the surface, so x equal to 0. Okay, and for long channel, it's psi s. Okay, and this term is negligible because L is short. I mean, L is long. In that case, this psi s is controlled by VGS, like we discussed in chapter 5. Okay, and then we say that it reaches 2 psi b is the threshold. But with the short channel effect, the second term is also important, which means that the combination of first and second term for short channel device can reach 2 psi b, the psi 2 reaches 2 psi b before the long channel psi s is equal to 2 psi b. So it means the threshold voltage becomes lower, of a short channel device becomes lower than a long channel device due to the second term called SCE. And so in this model, we focus on the second term, which can be shown to be a exponential dependence on length. Again, this is dimensionless parameter, L over lambda or L over 2 lambda. So you want this to be not to be too small. And because if it's too small and this term is too large, you actually want this exponential minus pi L over 2 lambda to be much less than 1. I think I talked about that. Yeah. Okay. So so this continues from this. Okay, we can write the second term in this form. That's still the exponential factor. And so we need L. We need this factor to be larger than pi, so that this is less than 0.043, because pre-exponential factor is 1.5. so that we need a much smaller vector in the last exponential expression to make this product less than tenth of a volt, which means that the VT didn't decrease too much. Okay, so the condition, the simplified condition is L larger than 2 lambda. So this vector is less than e to the minus pi. Okay. So that means L minimum is 2 lambda. Okay, so let's see, let's look at the question again. So how do we reduce that? Well, we need to make sure that L min or 2 lambda, you want L to be short, and then lambda has to go down. Okay, and let me see. Okay, that leads to the next question. That is, what's the not the next one, but question number 5. What's the scale length? What's the significance of lambda in control short channel effect? And that's answered here. Because minimum channel length for acceptable short channel effect is 2 lambda. Okay, so to make a short channel work, lambda has to be reduced. And so how does lambda relate to the geometry? It's given by this equation. This equation, the lambda is unknown, so it's implicit. So it has to be solved numerically. You'll see some of the exercise in chapter 6. You can try to solve lambda for given oxide thickness and the depletion width and epsilon. Okay, but the key importance is that lambda is longer than from this equation. Okay, it's from this equation. Both, so one angle is in the first quadrant, second angle is this, the other angle is in the second quadrant. Yeah. So one tangent is plus, the other tangent is minus. But so that means both angles are less than pi. Okay, if less than pi, that means lambda has to be longer than both WDM and TX. Okay, usually WDM is the longer one. So this is required. So if you just reduce TX, that's not enough, because then the WDM will just limit the lambda. Okay, and that's in this limit. Okay, let me see. Okay, so just to remind you that TX, of course, is gate oxide thickness, because it asks. Okay, what's related to geometry? Well, geometry is here. The TX and WD. Okay, so we discussed that in this case, in the straight line case. Okay, lambda is simply WD plus TX if the two direct constants are the same. So in that case, WD plus TX is the height of the rectangle. L is the width of the rectangle. Okay. So for short channel effect to be acceptable, L needs to be longer than 2 lambda, which means that channel length has to be longer than twice the height of this rectangle, TX plus WD. So it becomes a very simple geometrical point. That is, the aspect ratio of this rectangle. It has to be, the width has to be more than double the height. Otherwise, your short channel effect becomes bad. It's not good enough. Now, to reduce TX, of course, we just grow thinner and thinner, of course, until you have gate tunneling problem. Now, to reduce the depletion width, we have to increase the p-type for NFAT p-type doping. Okay, it goes as roughly as 1 over square root of NA. So to reduce WDM by a factor of 10, NA has to go up by a factor of 100. It's shown here. And so this goes up very quickly, very rapidly, and it becomes too high. And in fact, the threshold voltage. Okay, so we'll cover this part in the second half of chapter 6, actually later today. So how do we deal with this very high substrate doping? Okay, and the answer is non-uniform doping. We'll discuss that probably in the second or third period today. Okay, next question is about the velocity, NFAT and PFAT. Well, we covered it in chapter 2. So it's inversely proportional to effective mass. And we have shown here that for bulk, the whole mobility is about roughly a third of electron mobility because effective mass of holes are heavier than effective mass of electrons. Okay. And when we get to MOSFET, okay, this was discussed in chapter 5. Let's focus on the room temperature case. So, well, first of all, we see that the MOSFET mobility, this is for electron, is less than in the bulk silicon. Bulk is almost 1400, but for MOSFET, its highest here is 800. Okay, and this is because you have additionals. Because in the MOSFET, in the virtual layer, you have a lattice discontinuity. Okay, so the phonon in this case is different from the three-dimensional bulk case shown here. But as far as as far as electron and hole comparison, hole is still worse than electron. You can see this is only about 200 at the highest, the hole mobility at room temperature. In fact, we often get number of hole mobility less than 100 when we get to very short device. And so we have a factor of 4. Okay, 800 versus 200. Okay. So unless you have strained silicon, in that case, actually we can enhance the mobility of PFAT more than NFAT. And those two, NFAT and PFAT becomes more equalized. Those will be covered by Jackson, Sun Yuanzang. He cannot talk about it today, but in next Monday, he'll cover a session about high mobility or strain effect on NFAT and PFAT. Okay. Next question is velocity saturation again. Okay, so this from chapter 2. This shows in general that the low field, this is velocity field plot. Okay, at a low field, velocity is proportional to field, 45 degrees in the log scale, but it tends to saturate. And in chapter 6, we covered the model. Let's see. So this kind of relationship with n equal to some number larger than 1 has the property of as the shape of this dependence. At the low field, velocity proportional to field. At high field, velocity becomes constant, or saturation velocity. So mathematically, you can see that when the field is high, denominator becomes E over EC, and the velocity doesn't go up with field anymore. Okay, so this is a mathematical expression of this kind of behavior. And in chapter 6, actually just last class, we solved this in a MOSFET model. Right? So the velocity, in the chapter 5, the current is just given by velocity, and then only the mu dv dy. dv dy is field. But now we have for n equal to 1 model, you have a denominator, and that depends on the VSAT. Okay, so and so the model solved for the source drain current. The numerator is the same as long channel, and but the denominator is due to velocity saturation effect, which makes the current lower than the long channel value. Let's go back and see. And okay, so that's why it causes a deviation from long channel current behavior. So mathematically, you can see it's from this term that when L is short, okay, eventually, and also we show the chart. Yeah, I showed this chart earlier, but this comes back again. So when this term becomes important, the saturation current becomes independent of L. Okay, so that's the same answer to the earlier question. Okay, last question. How does drain DIPL impact the threshold voltage? Okay. Why is more pronounced in short channel compared with long ones? Okay. So DIPL essentially means at high drain voltage, the threshold voltage is lower, as shown here, okay, in this dashed case. And also schematically, you can see that if at a certain gate voltage, if the channel is long, like case A, then you can vary the drain up and down by changing VDS. A large VDS means you pull the drain down. But because it's long channel, so it doesn't affect the barrier height. But when you have a short channel like case B, then first of all, the barrier is lowered than the long channel case. And also you can see that if drain voltage goes up, VDS go up, you pull this down, you can see that it will affect the height, make the height even lower. Okay? So that's the concept. And mathematically, of course, again, we look at this this model. This model has this term is the short channel effect, and you can see the VDS dependence right here. Okay, so this means a high drain, you have a larger short channel effect because of the this factor here. And for long channel, it doesn't matter because of the e to the minus pi over 2 lambda term. So if you long channel, the whole second term is small. In that case, of course, it will not depend on VDS. Okay. So that's the answer to that question. More pronounced in short channel compared with long one. So mathematically, you can quantify how the VDS affect the threshold voltage or effect at the short channel, the short channel term when L is short. So when this is not very small, then it will depend on VDS. For long channel, the whole second term is not important. That's why there's no DIPL. Yeah. Okay, so I think I answered all the questions. Let's go on with where we left off in chapter 6. Okay. Okay, so this is where we left off last Monday. The so far with all the model, whether it's long channel or short or velocity saturation, is from driven diffusion. Driven diffusion assumes that you have a lot of collisions in the channel between source and drain. But for the channel is very short, the mean free path or the average distance between collisions becomes comparable to the channel length. In this case, the 30 nanometer. If the mean free path is 10 nanometer, then there are a lot of carriers that do not suffer enough collision to lose their momentum. So in other words, they occupy the states higher than the bottom of the conduction band. Okay, and so this so-called velocity overshoot. So some of the carriers here, they can actually move at velocity higher than 10 to the 7, shown here. Okay, so from the same Monte Carlo model, you can see the electron reaches 2.5 times 10 to the 7 at the drain. Okay, but what's this effect on the MOSFET current? Okay. In the next chart, first we look at even though the carrier electron velocity is much higher than the 10 to the 7 at the drain, but near the source, okay, source is here. Let me go back to here. Okay. This is the source, that's the drain. So at the source, it's only about between 10 to the 7 and 1.5 10 to the 7, but not much higher. Okay, so which means that the current does not greatly exceed the VSAC, which is given by 10 to the 7. So conceptually, this is the physical picture. We apply this the current expression. Current is always or current per width. You're always Qi times V. Qi is the mobile charge density per area, per gate area. V is the velocity of the carriers. So you can apply this to at any point in the channel, the source, the drain, or in between source and drain. Okay, and this has to be continuous. So it doesn't matter which point you pick. So we pick 2 points near the source and near the drain. Near the source, Qi, okay, is Cox Vg minus Vt. So we know Qi at the source, depend on the gate voltage over the threshold voltage, but we don't know the source velocity. Vs is source velocity. At the drain, the velocity is much higher than the source because of the acceleration, but Qi is decreased, okay, to Cox Vg minus Vd minus Vd set. Now in chapter 5 we have an m factor. Okay, so here we assume m equal to 1 in the ideal case. Let's to simplify it. But what this means is that the product of Qi and V must be the same. So near the drain, even though the Vd is much higher than Vs, but Qi is much less. Okay, so near the source, the carrier velocity is low, inversion charge density is high. Near the drain, the velocity is high, but the carrier density is low. Okay, so I would mention very simple analogy of traffic, car traffic on highway. Okay. So let's assume that so on a highway, you have a number of cars going at a certain speed, and the flux of cars, or the current, is the car density times the car velocity. Okay. So near the source, the car density is high, but velocity is low. Near the drain, the car velocity is high, but density is low, and the product is the same. In other words, you have a traffic jam near the source. Okay? When you have a traffic jam, the car moves slowly, but they are closer together, so car density is higher. At the train, when you get out of traffic jam, the cars speed up. They move faster, but the distance between cars increased. In other words, the density of cars is lower, and the progress is always the same, assuming that there's no entrance or exit of the highway. Okay. So that's the situation. And so from this picture, we go back to this case. Okay. So even though electron moves high, velocity is high at the drain, but the electron density is low. Okay. And so the current is really given by the electron velocity near the source, because here we know the emerging charge density, Cox Vg minus Vt. Okay. So based on this, if we know the Vs, we know source velocity, then we know the current. At the drain, you know the velocity is not enough because the charge is reduced by the minus Vd set term. Okay. In fact, the Vd set is going to adjust itself such that the product remains the same as the product at the source. Okay. So from this picture, our focus should be on the source velocity, because at the source, charge density is known. So if the source velocity is high, then you have a higher current. Okay, and right, so based on this picture, there was a publication on the so-called ballistic MOSFET model. It was published in 1990s, about 30 years ago. And okay, first of all, ballistic means that there's no collision in the channel. Okay. Now, if you use chapter 5, the current is proportional to mobility. Right? So if there's no collision, mobility goes to infinity, the current is supposed to go to infinity. But that's not physical, because even if there's no collision in the channel, MOSFET current remains finite. So this model tries to figure out, in the ideal case, if there's no collision in the channel, how much current can a MOSFET have? Okay. And we have actually seen such kind of treatment for Schottky diode in chapter 3. Okay. So it's like semi-ionic emission, which there's no collision as long as the electron energy is above the barrier, and it goes to the other side, contribute to the current. Okay. So the focus is on the electron distribution at the source here. But we also apply quantum mechanics, because we know that in a MOSFET, the electrons are very close to the surface. It's confined to the surface. Right? The field is very high. And so that in chapter 4, we mentioned that the there's actually discrete subbands. Okay? The lower subband is some energy above the bottom conduction band. Bottom conduction band we call EC prime. Okay? And the next one is EC prime plus EJ, J equal to 0, and so on. Okay? And in each subband, there's also kinetic energy. Okay? So first you have EC prime is top of the conduction band, and then you have the quantum mechanical subband energy, and then you have states. So this gray region means you have electronic states, and the electrons here, then it has kinetic energy. Kinetic energy means that you have a certain velocity. Okay. Now, so we calculate, okay, like before, current per width is velocity times charge. Right? The same thing here. Current per width is charge, mobile charge per area times the velocity. Okay. So, but both velocity and charge density depend on the kinetic energy, depend on the velocity. So we have to integrate. Okay, so we can see that first of all, this is I plus. Okay, I plus means that from the source to drain. Okay. So since there's no collision, so if you look at the source, all the electron with the velocity pointing toward the drain will make it to the drain because there's no collision. If it's collision, it can be scattered back. But if it's ballistic, then all the electron with a positive velocity at the source, okay, will make it to the drain. So that's why I say the integral is for positive Vy in the left to right direction. Okay, you integrate that. And there's also a z direction, which is, that doesn't matter, we just multiply by the width. And let's see. Yeah, so you can see that this is Fermi-Dirac distribution. Okay, 1 plus e to the e minus ef. So that's e minus EFS. EFS is the Fermi level for the source. And so that's the energy E minus EFS. Okay, and so that's the Fermi-Dirac, and the numerator is the density of states, two-dimensional density of states. I'm not sure I covered that in chapter 4, but you can look up in the book that the two-dimensional density of states actually is constant. So it's made it very simple. And then multiply by Vy because that's the flux. Flux is velocity times charge density. Okay? So it's integrate that. And so this is the positive going current. And okay, so this becomes, you can actually carry out the integration. I'm not going over the mathematical details, okay? And look at the book. This becomes a Fermi-Dirac integral f to the 1/2, okay, of, let's see, this is EF minus EC prime EJ. So EF minus this EC prime plus EJ. Okay. So this is positive going. And so what about negative going? Well, negative going, because there's no collision. So the current not going from drain to source must come from the drain. So we apply the same expression to the drain with negative going velocity, but the Fermi level is FD. So we replace this Fs by FD, which is lower than EFS by VDS, the drain source to drain bias, right? And so this, if VDS is high, then this is very low, and that's the negative going current. Okay. And so in other words, if we look at the entire picture, the net current is I plus minus I minus. Okay. I plus is due to the electron near the source with a positive velocity. I minus is due to the electron from the drain with a negative velocity. Okay. Now, of course, if EFD, well, first of all, if EFD is much lower than EFS, then I minus is negligible. Okay, so the current is then I plus. This means that it's independent of VDS. So the current saturates. Of course, if VDS equals 0, then EFS and EFD are the same, which is what we expect. If there's no source drain bias, then the source drain to left to right current equals right to left current, and they cancel each other. Okay, so at the VDS equal to 0, I plus equal to I minus. But when VDS is high, I minus become negligible. So the MOSFET current is given by I plus. All right, so based on this, we can actually derive what ballistic MOSFET, the IDVD characteristics. Okay? That has to be computed numerically. Okay? But let's look at the result. First of all, current still saturates, but for a very different physical reason. Okay? In chapter 5, we talk about saturation due to pinch-off. Okay? In chapter 6, or the earlier part of chapter 6, we talk about the current saturates when the velocity at the drain reaches saturation velocity. Okay? But those are all based on different diffusion model. That assumes a lot of collisions between the source and drain. When the MOSFET is very short, ideally you get to ballistic limit, in which that there's no collision between source and drain. Okay, so in other words, channel is much less than the mean free path. But in that case, so this model will point out that even in that case, the current still saturates. Okay, but for a different reason. The current saturates because, go back to this picture, because we already collected all the current from the source. Okay, and the current from the source is I plus term. It's independent of VDS. And so it doesn't matter what the VDS is. The current is constant. We only depend on the gate voltage. Okay, gate voltage, of course, will control the EC prime here. Okay. So that will control the current through that way. But current is independent of VDS. But when the drain voltage is low enough, then you have a cancellation between I plus and I minus. And eventually, of course, I plus equal to I minus when VDS equal to 0. Okay. So that means that when VDS equal to 0, there's no current because I plus equal to I minus. As you increase for a given VG minus VT, as you increase the drain voltage, okay, I plus doesn't change. I minus will decrease until when I minus becomes negligible. So the current is given by I plus only, and that's when the current saturates. Yeah. So the physics behind this the saturation of ballistic MOSFET is very different from the current saturation in the driven diffusion model. Okay. This actually can be further simplified, okay, assuming that again, I'm skipping skipping over all the math. You can read the book if you want to follow the step by step. But basically, it's two Fermi integrals. Okay, one is VDS dependent. So when it's large enough, the second Fermi integral becomes negligible. The current is only given by the first Fermi integral, and that's VDS independent or saturates. It actually has a very simple expression for the saturation current. Saturation current is only given by the first Fermi Dirac integral. So I just said that because the reverse injection I minus becomes negligible. So this is the maximum current you can expect of a MOSFET, even if there's no collision in the channel. So even if your mobility is infinite, there's no collision, but the current is still limited by the velocity at the source. Like in this case, the Vs has a certain limit. Okay, and that's you can see that the current per width, these are all fundamental constants. Okay, and the only VGS the only VGS dependence is here, and that's 3/2. We can understand this why the 3/2 from this picture. Okay, now so the current is given by this term, WC Vg minus Vt Vs. So we have one Vg minus Vt factor from Qi. Okay. But the other, but at the end, you have 3/2. So there's a square root of Vg minus Vt. And that comes from the Vs vector. Okay. Because Vs is this picture. Vs is the average velocity, carrier velocity near the source. And the average velocity at the source depend on the density. Okay? Because, again, let's go back to the basic picture here. Yeah, let's go to the picture. So you can see that the electron at the source are occupy the lowest state that's available. But since you cannot jam all the electrons at the lowest state, so the electron has to go up. When you have a higher electron density here, okay, because that means the higher and higher energy state at higher energy are occupied. So you can see that the average velocity of electron at the source depend on the density. The higher the density, the higher the carrier velocity. So this sort of explains quantitatively why the Vs has the square root of Vg minus Vt dependence, which makes Vg minus Vt to the 3/2 here. Okay, so we take a 20-minute break here. We'll resume at 10:10 your time. So this wraps up the ballistic MOSFET. And next, we talk about the MOSFET design, threshold voltage design. Okay, so we'll continue in 20 minutes.
Okay.
Okay, we resume the class. Okay, the next section in chapter 6 deal with the MOSFET design, namely threshold voltage design. And this shows the MOSFET current as function of gate voltage in two scales, log scale and linear scale. It's the same data, same curve, but because the if you look at linear scale, okay, it looks like VT is somewhere below 0.3, and then current starts to flow once you are above 0.25 or so VG. But actually, the current doesn't go to zero, as we know that it goes down exponentially. So that's why we need a log scale to see how this current is behaving. Okay, but in the log scale, above threshold, the current doesn't change much. So we need to use a linear scale. So in this case, we can define I on and I off, assuming a power supply voltage, in this case, 1.2 volt. Okay. So zero, the current at zero, we call it I off. In this case, it's 10 nanoamp per micron. And the current when VGS equal to 1.2 or VDD is the on current. Okay. And so in other words, the swing between off and on is VDD. Now, when we change the threshold voltage, you basically shift the curve, both curves. Okay, if it's a lower threshold voltage, both curves shift to the left. And if it's a higher threshold voltage, both curves shift to the right. So threshold voltage is basically, let me see if it's okay, it's the same. It's the same plot. I mean, let's still use this. So if VT is too low, then the on current is good, but off current is too high. If VT is too high, off current is low, but on current is too low. Okay? So both IR depend on threshold voltage. Okay? So how do we choose the threshold voltage? We base on the off current. Okay? Off current in chapter 5, the subthreshold model, okay, give you this kind of off current, and roughly it's 1 micron per micron at the threshold at VT, right here. But we want I off to be less than, no higher than 10 to the minus 8 or 10 nanoamp. In that case, the VT needs to be at least 0.2 volts, as shown here. So this is a little bit higher than 0.2. So from an off current point of view, because in a silicon chip of something like 10 or 100 billion transistors, okay, all the transistors will have off current, okay? And so they add up. That's why we have to, even though off current is negligible in a single transistor, but for the whole chip, it can add up to 10 watts or even 100 watts if the VT is too low. Okay? So this requires a minimum VT of 0.2 volt. On the other hand, if VT is high, then we have a circuit delay problem because basically when you turn on a MOSFET, you try to discharge a capacitor, then the charging or discharging rate, okay, C dV dt, is given by the current. And the delay, okay, if you multiply dt here and divide the current to the other side, and then we integrate, you get a delay time. So delay time is basically CV over I, over I on. So on current cannot be too low. And that means the threshold voltage cannot be too high. In this particular case, we can see that this actually is sort of, we'll go in more detail in chapter 8. Okay? But we can see that depending on the choice of VT, that this is one inverse of delay, so 1 over delay. Okay? So that means delay becomes longer and longer if VT or VDD goes up. So typically we require VT or VDD less than 0.3 volt, so that the delay or 1 of delay is not too small. Delay is not too large for this case. So basically we have threshold voltage is basically on off current trade-off. But I want to point out using this chart that the trade-off is not the same I-on-I-off ratio, because we know the off current, okay, is exponential. If you, let's say you change the VT by incremental delta VT, let's say it's positive, then I-off will decrease by a factor of Q delta VT over MKT exponential factor, because of the, when you shift the curve, okay, VT is larger than 0 means you shift both curves to the right, to the positive. So off current goes down by exponential this factor, where this is given by the subsocial current slope. But on current is not by factor; it's increased by amount. Okay, amount of GM is transconductance. GM is DI, DS, dVGS. In other words, the slope here, the saturation current as function of the VGS slope here is GM. So if you increase the threshold by delta VT, the current will decrease by GM delta VT. Okay. So this just shows that the trade-off between I-on and I-off is not such that you have the same ratio. You can see that if you want I-on/I-off ratio to be large, then the best way is to have IVT, because the off current goes down exponentially. Okay, on current even though it goes down, but it only goes down by an amount. Okay, so the best I-on/I-off ratio is such that the whole IB curve in subthreshold, because then the current is an exponential function of VGS. Okay, but that's too low. That current is too low. We will go over in chapter 8 that it's not a good idea to operate a MOSFET below threshold because there are certain capacitors that the parasitic capacitor has to be charged and discharged at a reasonable rate. All right, so now actually you can see that this is actually from publication early day from Intel. You can see that they don't even talk about threshold voltage. They just plot off current versus on current. Okay? And so you can see that over the chip, you will measure many points. That means the threshold voltage or the channel length is different. Okay? So you can see off current is log scale, on current is linear scale. Okay? It's the same as what we are talking about here. On current is linear scale, off current is log scale. Okay? And so they draw a line here. This drawing line, this is 109 per micron. So off current cannot exceed that. That gives you the on current value for this particular off current is 1.46 for this design and 1.75 for the other design. And all right, so threshold voltage is not theoretically not intrinsic to the device. Okay, it's basically some label that allows us to determine the off current and on current, and they are correlated in this fashion. Okay, so next we consider schematically so-called MOSFET design space. Okay, this design space is we plot a plane with TX going vertically and WDM going horizontally. Okay. So first, we consider, let's see. Okay. First, we consider this line. Remember the substitute swing is MKT over Q. This is KT over Q times log 10. Right? Okay, that's 60 millivolts, but multiplied by the M. And then we say that M cannot be too high, or M minus, or let's say M equal to 1.4, okay? Which means that M is 1 plus 3 TX over WDM. So if M is 1.4, M minus 1 is 0.4, that means 3 TX over WDM is 0.4. And that's represented by this line through the origin. And we want this line here. We want to the left, upper left of this line, which means that the substitute swing is not worse than 1.4 times 60, which is about 84 millivolt per decade. Okay? So we have to stay to the right, lower right of this line. Here. That's first consideration. Second consideration is from short channel effect. Remember that lambda, in the case of very thin oxide, can be approximated by lambda equal to WDM plus 3TX. And then we say the channel length has to be longer, cannot be shorter than 2 lambda. So in other words, this lambda equal to L over 2. And for given L, if you go to the upper right of this line, okay, that means this line is represent WDM plus 3TX. So with this is a sort of a negative slope. Okay. So beyond this line, we have a poor short channel effect, which means that the lambda is too large. Okay, beyond this, the lambda is larger than L over 2. You have to stay to the lower left, which means that lambda is less than L over 2. Okay, or L is longer than 2 lambda. Okay. So this line is from subscale swing point of view. This line is from short channel effect point of view. And those two will intersect at this point. That defines the maximum oxide thickness. Okay, so you can solve those two equations. And then we derive that this point is actually L over 20. Okay. So this shows that the oxide cannot be thicker than L over 20. Okay. So let's say L is 20 nanometer. Then L over 20 is 1 nanometer. So that means for 20 nanometer MOSFET, the maximum oxide thickness is 1. And in 1 nanometer, of course, we have and then we have a quantum mechanical tunneling problem. Or conversely, if Tox cannot be thinner than 1 nanometer without the high K, then the L is limited to 20 nanometer. Okay. And in practice, we stay with oxide until I think L equal to 50 nanometer or so. And then we switch to high K. Okay. And that's given by this line here. This line is define the minimal oxide that below which we have oxide breakdown. For given supply voltage, you cannot make the oxide too thin. If it's too thin, then you have a breakdown problem. So based on these three considerations, we'll define a triangle area in this gray region that is the allowable design space. Okay? So you have good subscale swing, good short channel effect, and oxide is reliable. It doesn't break down. So we come back to this maximum oxide, which we have solved. We have solved, given by this. So, so we consider this point double okay. So this means that this breakdown, this line cannot be above Tox max. If above that, then you have no design space. So this has to be below, which requires the supply voltage to be less than the maximum field. Let's see, maximum field times Tox. Tox is L over 20. Okay. Tox maximum is L over 20. Okay, so this simple equation says that that's the maximum supply voltage VDD. And so we consider a couple of cases. Okay, when the oxide thick, 20 nanometer, usually we say the maximum field is 2 megavolt per centimeter, above which you have an oxide breakdown probability. Okay. So we put in this equation, E ox is 2 megavolt, okay, divided by 20, and L, okay, and let's say for this oxide, we can make L of 1 micron, 1 micron MOSFET. So this says that VDD is less than 10 volt. Okay, so for 1 micron MOSFET, we use oxide of 20 nanometer. Supply voltage needs to be less than 10 volt, which is no problem. In practice, it's 5 volt, okay, which satisfies this criteria, this upper limit. But when we have L equal to 50 nanometer, Okay, we need an oxide of 3 nanometer. Okay, and fortunately, thinner oxide actually can go to higher field. Okay, so for 20 nanometer or thicker oxide, the field cannot exceed 2 megavolt. But for 3 nanometer, the maximum field can go up to 5 megavolt. So if we put in those numbers, this means that if L is 50 nanometer, VDD needs to be less than 1.25 volt. We can see that the window becomes smaller when you go to thinner oxide and shorter channel lengths. Okay, and so it's fortunate that for thinner oxide we have a higher maximum field, which allows us to make this 50 nanometer with supply voltage sort of between 1 volt and 1.5 volt. Okay, and that satisfies this. We have a finite design space for this case. But if you go even further, okay, we are now below 20 nanometer. So you can see that we are sort of running out of room here. Okay? And even with high K. So in general, we can summarize these points are actual data points from the actual industry technology. Okay? So we plot versus channel length, the supply voltage, top curve, okay? The structural voltage, second curve, the oxide thickness, the voltage used the left scale, oxide used the right scale. So again, for 1 micron MOSFET, that's the right side. VDD equal to 5 volt, then VT equal to something like 0.7.8 volt. Okay, that's no problem. But now we shrunk to 20 nanometer. Oxide becomes, this is angstrom. So this is 1 nanometer thick oxide. And remember that VT cannot be below 0.2. So let's say VT, so that's why this curve sort of saturate, the downward trend will saturate about 0.25. But that means VDD cannot decrease too much. If it decreases too much, then the VDD or VT ratio, in this case, is a factor of 4. Okay, the ratio is, if the ratio is too small, then you have a performance problem. Okay, so you want switching speed problem due to the current. Okay, so this is on current issue. So basically, that's the scenario that depicted here. But so the oxide trend is more or less proportional to channel length, okay, as we expected from the scale length model. But the VDD and the VT, they are not straight line at all, mainly because the off current doesn't scale. So VT has a minimum requirement about 0.2, 0.25 volt. Here's another consideration from the power point of view. There are two kinds of power: active power and standby power. Okay, active power is when the MOSFET is turning on off to switch to the next logic circuit. Okay, so it's switching. And standby is the MOSFET is not switching, but the off current will dissipate certain power per transistor, and over the whole chip, the standby power can be appreciable. Okay? And so again, conceptually, we have a power supply voltage vertically, structural voltage horizontally. And to get performance, we want VT and the VDD ratio to be small, which means that we want to push to the upper left direction. Up means higher supply voltage. Left means lower threshold voltage. Okay. But the power will go up if you move to the left. Move to the left means lower threshold voltage. Then the standby power goes high. Okay, proportional to e to the minus q VT over MKT. Okay, so standby power go up exponentially than when the threshold voltage is reduced. On the other hand, if you increase supply voltage upward, then the active power, CV square F, okay, will go discussed in more detail in chapter 8, okay, a higher active power. So to push performance, the power has to go up, either the standby power or the active power. That's why the recent today's logic chips or microprocessor chips are all power limited, okay? Because to get the performance, some power has to go up. We mean both power has to go up from the VDD VT point of view. And this also leads to the trend of a multiple threshold voltage in today's technology. Okay? So we offer multiple threshold voltage so that depend on the circuit. If the standby power is more important, okay, then the circuit use higher VT. If the switching speed is more important, then the circuit use low VT. Okay, so any of today's technology will have a multiple threshold voltage, and so that, for example, in the memory cell, which doesn't switch very often, but the standby power is important. So for those, we have high VT. But for the clock circuit, which is goes up and down every clock cycle, okay? So we want those VT to be low so that the clock circuit can go fast. Okay? And some technology can even offer 3 or more. Well, when we say 3 or more, for CMOS, it's like 6, because 3 for NMOS and 3 for PMOS. High, low, and the medium, and the middle. Okay? So this trends point out that we have to move to multiple threshold voltage in the CMOS technology. Okay. So that's from the circuit point of view. And now from a device point of view, how do we design the device to deliver the threshold voltage that we want? Okay. We showed this chart in chapter 4, I think. Okay. So we say that chapter 5, the threshold voltage, there are 3 terms: flat band voltage, 2 psi B, and last term is Vox. Vox is the potential drop of glass oxide at threshold voltage. And this is good even to QD over Cox, because at the when gate voltage at the threshold value, the most of the charge in silicon is depletion charge. It's not immersion charge. Okay, after the threshold voltage, the immersion charge goes up. Okay, but at threshold, the charge in silicon is still dominated by depletion charge. Okay, so basically, threshold voltage has 3 terms: B flat band, 2 psi B, and the charge, depletion charge over Cox at threshold. Okay. Now, of these 3 terms, the second term it's pretty much fixed. It's about 0.9 volt or 1 volt. Okay. Now, since VT, we just showed that the VT has to be less than 1 volt. So we need V flat band to be negative. Okay. Since this is about 1 volt, so we make V flat band of -1, which means the N plus silicon work function for metal gate, it's N plus silicon work function. Okay. For polysilicon, it's N plus poly on NFET, and P plus poly on PFET. So that the first and second term more or less cancel. So now the third term is the one that determines the VT. Okay. So if you choose the right work function, even with metal gate, we call it the replacement gate. Okay. So even we move beyond the poly, but we still need the work function to deliver the N plus silicon work function for NFET and P plus silicon work function for PFET, so that these two terms add up to cancel each other, and VT is controlled by the third term. Third term is depletion charge over Cox. Okay. So we focus for the threshold voltage control or design, we focus on the third term. Okay. And now so far in chapter 5, we only consider uniformly doped MOSFET. Let's say it's NA. Okay. And then we derived the maximum depletion width. Okay. Is this is 2 epsilon silicon 2 psi B. Okay. So it's 4 epsilon silicon psi B. That's the maximum depletion width. And threshold voltage, the third term is the depletion charge. The depletion charge is QNA WDM. QNA WDM is equal to that. Okay. So for uniform doped case, both WDM and VT are determined by NA. If you choose NA, then both WDM and the threshold voltage are fixed. And there's no other adjustable parameters. And that's not good enough. Okay. Because as we see that and we want to adjust VT so that it goes down. It's the channel length goes down. Okay. Okay. Actually, this can also be expressed in this form. Yeah. So we can actually eliminate NA. Okay, you can solve NA and then put it in here. So this becomes 1 plus 60 R to psi B. So now you can see that for uniform doped case, 2 psi B is about 1 volt, and V flat band is -1. So there's no other parameter that we can control. But ideally, we want to be able to control the flat band, control the WDM for short channel effect, but we want lambda to be, well, let's go back. Okay. Or to control the scale length, we need to bring WDM down. It's higher and higher doping. Okay. But So when NA is high, then the threshold voltage can be too high. And so if NA is enough to control the short channel effect with small WDM, then the VT is not as low as you want it to be. So this point out that we have to employ non-uniform doping. Okay? Uniform doping, you just run out of room, and usually the VT is too high. Okay? So non-uniform doping allows us to have additional parameter in order to control the WDM and therefore the scale length and the VT independently to some degree. So this chart treated in general non-uniform doping. So assume that you have a doping concentration instead of uniform, you have a constant. You have n as function of x. X is in the depth direction. Yeah. So 1D Poisson equation. Okay, this diffusion, the charge density is diffusion charge only, because at threshold, this mostly the diffusion charge. There's no inversion charge. So we can integrate this equation once, and then we get the field. We integrate from, so this is field at x. Okay, we integrate from x to WD because we know that the field is 0 at the diffusion boundary. Beyond WD, there's no according to the depletion approximation, beyond depletion width, there's no the charge is neutral, right? And so integrate from WD to x, and I build up the field at x. Okay, so that WD is the integration limit, and we integrate again. We get the potential. This is the second order. Integrated once, integrated second time. So now we have a two integration of this. NX is the assumed doping profile, non-uniform doping profile, and you integrate this twice, it becomes a double integral. Okay, and this can be reduced to a single integral. The mass is shown on the next chart. So if you have this double integral, we do by parts, integration by parts. Okay. So that this integral of f prime g becomes integration of f g prime. Okay. F is x, the prime is 1. Okay. And g is this inner integral. So g prime is just nx. So by doing this, you convert the double integral into a single integral of x times nx. We go back. Okay. So the math explains why I can get this expression, which is single integral 0 to WD, but instead of nx with x nx. Okay. And that's the surface potential. Okay. So to get the maximum diffusion width, we do this integration until psi s equal to 2 psi b. Okay. So we integrate this doping profile deeper and deeper from 0 to the diffusion boundary. So the psi s goes up until 2 psi s equal to 2 psi b, and that's the threshold condition. And WD becomes WD maximum diffusion width. Okay. So for a given doping profile NX, first we solve this to obtain the WDM. Okay, so with that, this equation equal to 2 psi b, which is fixed, and then we get the WDM. Okay. Once we have WDM, we put it back. We put it back, and that will determine the diffusion charge density. Okay. So we needed to, for a non-uniform dope MOSFET, we need to know the integral. This integral, that's the diffusion charge density is epsilon silicon times field. Right? So it's Q integration of Nx from 0 to WDM. Okay. And also we need a second integral of we call the first moment of Nx, or Nx times x, the second one. Okay. Okay. So let's look at a simple example to understand this point. Okay. So this is very simple profile, high-low. The Nx is function of depth. Is the step function near the surface. Assume it's high, and then drop to Na. Okay. And okay, so let's go to next chart. This is some math. Okay, so first we need to integrate x and x to get the surface potential. Okay. X and x, we decompose the integral into two integrals. From 0 to xs, well, doping is Ns. And from xx to WD, well, doping is Na. Okay. And in both regions, N is constant. Okay. So in the first region, 0 to xs is x times Ns. In the second region, xx to WD, doping is Na, so xNa. So we can derive this result, and then we can solve this equation for WD as function of psi s. Okay, now remember that. Let's see. First, we solve this for psi is equal to 2 psi b, and then solve WDM. Okay. So we let psi s, well, this is still psi s, we let psi equal to 2 psi b, and then we solve WD. Okay, that's shown here, okay, from this equation. And then we know the threshold voltage, okay, because VGS is V-flat band plus the 2 psi b, and then plus the last term is the diffusion charge in silicon. Diffusion charge from 0 to WD. Okay. The first part is Ns up to the depth of xs. So in other words, the area under this curve. Okay, that's QD. Okay, this is per volume. We integrate in the depth direction. We have charge density per area. So it's Q Ns times xs. That's first rectangle. Second rectangle is QNA times WD minus XX. Okay. Okay, so from here, we can see that the diffusion, the threshold voltage is when psi is equal to psi b past that. Okay, so we go back to this chart. So WDM is solved by this. This is equal psi s equal to psi b. It's from here. We let psi s equal to psi b, we solve WD equal to WDM here. And then we put that into the threshold. So that's WDM, WD, right? And then this is diffusion charge density. Oh, okay, so this is this region. Oh, go back here. You can see that's it's Q. So this is equal to QNA WD plus that. Right? QNA WD. Okay, put this in here. And then plus the additional charge is NS minus NA times XS. Okay. So for this high-low doping profile, when we reach the 2 psi b condition, we have a higher threshold voltage than uniformly doped NA case. Okay. You can see that by putting additional doping at the surface, it increases the threshold voltage, increase the third term by this amount because we put in additional charge, NS minus NA from 0 to XS. That's basically that. Okay? So this allows us to, we go back to the, so we go back to this. That's for uniform, but not for non-uniform. Now we can, for a given WDM, we can have a different VT because we have additional parameters. Okay. Now, there's one issue that needs to be discussed. That's 2 psi b. Because we use 2 psi b when the doping is uniform. But now doping is not uniform. So which psi b do we use? Okay. Actually, 2 psi b should not change too much. So I have a chart to explain. So what is 2 psi b? And what about V flat band? Yeah, we define V flat band using uniform doping, but now you have a non-uniform doping. So, so how do we deal with that? Okay. So we go back to the original. Why is it 2 psi b, which is not a unique choice? Okay, because basically we're saying that psi b is the Fermi level below the mid gap in the substrate, and then at the surface, the Fermi level becomes above EI by the same amount of psi b. That's where the 2 psi b come from. But that's not the key. The key is the electron concentration. Electron concentration is given by the expression EF minus EI. EF minus EI. In this case, EF is higher than EI, okay, by psi b, but it doesn't have to be psi b. It's best to say that they equal to this equal to Eg over 2, which means that the Fermi level becomes the same as conduction band. You can see that if you bend the conduction band to EF, then the electron density will go up. Okay. So 2 psi b, usually we say it's 1 volt or 1.9 volt, whether it's uniform or non-uniform. That's sort of close enough to the actual case. Okay. And so that explains the 2 psi b part. Okay. And so this is the result for if you want a higher threshold, you put in a high-low doping. But in practice, as shown here, usually you actually want a lower doping, lower VT. So it actually is not instead of high-low, which increase the threshold voltage, we actually want a low-high to get a lower threshold voltage. Shown here. Okay, so we take a 10-minute break and we'll continue 11:10. Restart. Okay. So to lower threshold voltage, we need a non-uniform doping, and that's low-high. Like in this case, the deeper down you have a higher doping, the surface lower doping. Actually, all the equations we divide for high-low works for low-high as well, because all that matters is that NS is lower than NA. So that in that case, this is actually, let's see, NS is lower than NA, so this is negative. And so that's a plus sign, but this is a minus sign because NS is lower than NA. That's negative. And that brings down the VT. Now, to simplify the math, okay, we let NS equal to 0. So in other words, we have undoped surface region of depth and excess. Okay, then simplify the maximum diffusion width to this equation, the square root of the XS squared undoped plus this term. And the VT is also simplified to this form with NS equal to 0. Okay. So this is just for simplification. Okay? And because once you have low high, the NS is much lower than NA, it doesn't matter what NS exactly is. So we may as well make NS equal to 0 to simplify the equations. So this will lower, give out a lower VT. And in particular, now notice, let's look at the maximum diffusion width, square root of 2 times. Okay. Undoped region, and the first time it gives you the maximum diffusion width. Now, if NA is very high, the first term in the square root will become small. Okay, then the diffusion width is simply given by XS. Okay, so in other words, if the substrate doping is very high, and we have undoped region, surface region of XS, then the maximum depletion region is just given by XS, the undoped region depth. In this case, we call it extreme retrograde. Low high is also called retrograde. So in this limit, the we call this I means intrinsic, 0 doping. If there's no doping, then there's no curvature, so slope is constant in this region. And then let's see, go back here. So in that case, this is negligible, but here you have to expand because you have the zero order will cancel, so we need another term. And the result is here. Is the Vt equal to this. Again, this is a 2 side base psi s. And then the diffusion charge is given by that. This actually can be easily understood from here. Okay, so here, xs and WDM is the same thing. So we have the bending here, but it's a straight line because there's no doping. So field is constant. The field is constant, and the potential, the bending is 2 psi b. So the field is simply, the slope here is 2 psi b divided by xs. 2 psi b divided by xs. So that's the field times epsilon silicon from Gauss law. That's diffusion charge density. That's the slope. Slope is 2 psi b divided by xs times epsilon silicon. That's the third term. Okay. And the Vt, okay, Vt by, like I said, you do a expansion and keep the zero and first zero order term cancel, and the first order term give that. Okay, so let's look at the situation. Okay, so in extreme retrograde, or some people call it ground plane. It means the same thing. The diffusion depth is the same as the undoped layer thickness. In other words, WDM and XS are the same. But where's the diffusion charge? Because it's undoped, so there's no diffusion charge. So where is this diffusion charge come from? The diffusion charge actually is located right at the WDM when the slope changes sign. Okay, from a field, some field to zero field. Okay, so there's a delta function of diffusion charge. Okay, so in other words, the charge looks like this. The gate charge on the gate equals the charge in silicon. Charge in silicon as inversion charge at the surface and diffusion charge. But remember that when it's uniformly doped, diffusion charge is uniformly from 0 to WD. But in this case, all the diffusion charge are at the boundary of the undoped, the depth of the undoped layer, or I layer, like a delta function. And also the magnitude of diffusion charge is the magnitude of charge given by the slope is 1/2 of the uniformly doped value. Okay, this is better understood from the next chart, which depict the band in three cases. First, uniform solid line. Solid line, we say that you bend by all the cases has the same 2 psi b, which is roughly 1 volt, and same WDM, okay, for the same scale length, lambda. And so for uniform doped, you go from here, and you bend 2 psi b to the surface, but it's parabolic. Okay, that's uniform doping. For ground plane or extreme retrograde that we just discussed, in this case, the field is constant, so the slope is constant. That's dashed. So we know that the field, the slope here, is 1/2 of the surface field in the uniform doped case. Okay, because this is parabolic and this is straight line. So the slope of the parabola is twice of the straight line. Okay, and that's what the factor of 2. See, the magnitude is 1/2 of the uniform doped value. In fact, you can compare this with the uniform doped case that we discussed before. Okay, when we say uniform, the VT is V flat band plus this 1 plus 6 TX over WDM to side B. But for the ground plane case, instead of 6, it's 3 because we reduced the depending charge density. To side B, 1 is the psi S to side B. We reduced the depending charge from 6 to 3 TX WDM. So that's why we have a 3. The factor of 2 come from the slope change. So for the same psi S, same depth, make a straight line undoped. It's half of the slope at the surface than the parabolic uniform doped case at the surface. Here's another way of looking. Okay. Instead of plotting the field, the potential, we plot the electric field versus depth. Okay. Field is the slope. Okay. And uniform doped case is here. Okay. The slope at 0 at the diffusion boundary, and it goes up linearly toward the surface. Okay. Remember that the surface field determines diffusion charge. So the third term, diffusion charge, is given by the y-intercept of this curve. So that's uniform doped case. And for the ground plane or extreme retrograde, the field is constant. That's the straight line here. Field is constant. But under the curve, if you integrate the field over depth, that's to psi B. So area under this curve and under this is always to psi B. Right. And so now we can see why the intercept here is only half of uniformly doped case, because the area of this triangle is the same as the area of this rectangle, which means that the triangle, the surface field has to be twice of the surface field of the rectangle shown here. Now also shown here is the third case. We call it counter-doped case, because you see that you can, so this field, okay, the field actually can be 0 if you counter-dope it. Yeah, because all you need is to have a 2 psi B band bending between the surface and the maximum diffusion region. Okay. And so by going from uniform to ground plane, we managed to reduce the surface slope by a factor of 2. But we can actually make the surface field go to 0. And that's this case. If the surface field is 0, then Vox is 0. Okay. Remember, Vox is the field times oxide thickness, right? So if the field is high, then Vox is high. And then by reduce the field by a factor of 2, we reduce Vox by a factor of 2. If I reduce the field to 0, then Vox is 0. Okay, so in that case, the threshold voltage term, we go back to this case, this term is 0 in the counter-doped case. Okay. And in terms of the field versus depth, that's this dashed, this dashed line here. So the field is 0, which means 0 intercept against the same area. The area is over 2 psi b. So all these have the same 2 psi b area, but different slope at the surface, different field at the surface. And also, you can see that the doping has reversed. Okay. Remember that the doping is the second derivative of potential, or first derivative of field. So uniform doped, that's p-type. But counter-doped means n-type. So the slope has changed. So in other words, this can be achieved. So we go from p-type to undoped to n-type. Okay. P-type, undoped, and n-type. So when you get to the n-type, there's no depletion charge at the threshold condition, ideally. But we have to be careful, because in that case, right, so we say the field is 0. But if you overdo it, then the field actually can be negative. It's shown here. And so now the field actually is negative. So now we get a buried channel device, because the channel is now not the surface, but rather below. That means we'll lose charge, because this charge is further away from the gate. Okay. So even though theoretically it's possible to have a shallow counter-doped, but in practice, we have to watch out to end up with a buried channel device. And also, it's hard to control the diffusion width to contain the short channel effect, the lambda question. Okay. So actually, I think in today's technology, there's some kind of counter-doping, but not to the extent that there's some counter-doping to get an even lower threshold voltage than the ground plane, but not all the way to the 0 depletion charge, like shown here. That's the ideal case. Okay. All right. Now let's look at the I call the channel profile evolution. Okay. This shows from 1 micron to half micron, 0.2 micron, 0.1 micron, and 50 nanometer. Okay. For the doping profile will change. For 1 micron is high-low, because here the channel length is long, so you don't need very high doping to control the lambda, the scale length and short channel. So let's say 10 to 16. At 10 to 16, the VT is too low, because we can have VT of 0.7. Remember that. For 1 micron, the VT can go up to 0.7, 0.8. Okay. So uniform VT is too low. So we can add a little high-low to make the VT the value that we desire. For half micron, we need higher doping, 5E16, to control the short channel effect, control the scale length. In this case, the VT is about right. So in this case, the uniform doping happened to satisfy both the scale length and the threshold voltage requirement. Okay, so remember here VT we need about 0.5. Half micron. Okay, about half volt VT. The threshold voltage is 3.3 volt. I mean the supply voltage is 3.3. Okay, this is 0.5. So in this case, the uniform doping can get the job done. But once you are below half micron, 0.2, now we need much higher doping. Let's say 3 times 10^17 to control the short channel effect, the scale length, to reduce the maximum diffusion width. So in that case, VT is too high if it's uniform. So this becomes low, high, or retrograde to bring the VT 0.2 micron, let's see, 0.2 micron. Okay, VT is about 0.35. Okay, and supply voltage is 2.5, and something like that. In this case. Now below that, of course, we can have a ground plane or extreme retrograde, and even counter-doped, below 0.1 micron and below. But in addition to that, we also have halo. Okay, halo is different type of non-uniform doping. Okay. The first three, high-low, uniform, low-high, those are one-dimensional, vertically non-uniform. But once you have halo, you have vertically non-uniform and laterally also non-uniform. Okay. So halo means not only is low-high doping, but also the doping is higher only near the source and drain. Okay. And if you go further beyond, the doping can be zero in the center. So most of the doping are near the source and drain. I call it the super halo. Okay. And okay, I explain how that works. But let's look at the first three. Why is this trend? High-low. Okay. We go back to this uniform channel doping case. Okay. And if it's uniform, it looks like that, and 2-side doesn't change much. TOX and WDM scale the same way, so the M doesn't change much. Reflect band is like a -1. So if it's uniform, VT doesn't change much. Okay, but we want VT to go down. Remember that. VT is we want to go down. So uniform doping. So for uniform doping, VT doesn't change much. Okay. Another factor is the quantum mechanical factor, because once the oxide thinner, channel length is shorter and oxide thinner, then we have a quantum mechanical ground state energy. Basically shift VT up, because 2-side is not enough. Remember we covered that in chapter 4. So now we need to have a bending, something like 10^4 or 2/10 over 2-side to get the threshold condition in the presence of quantum impact. So if you do uniform, actually the VT is going up instead of going down. So that's why we use non-uniform doping. So the 1D, this explains the trend from high-low to uniform to low-high. But that's all 1D vertically non-uniform. Okay. And the last two are laterally non-uniform. And here, this is how it works. We'll call it halo, because it's like related to the source and drain. Now, this kind of laterally non-uniform doping has to be done differently. Okay. For vertical non-uniform, that doping was introduced before the gate. In other words, all this doping is done before the gate is deposited. So it's uniform in the lateral direction because there's no gate and no source drain. But if you put in the p-type doping after the source and drain, then it becomes self-aligned to the source and drain. Okay, so that's what halo implant meant after gate patterning. So self-aligned to the gate. Sometimes people use angled implant. In other words, after the gate is patterned, we do the source drain, and then we shoot p-type doping at an angle to get this high, so-called high pockets. Some people call it pocket doping, or we call it halo doping. So these two regions are self-aligned to the source and drain, just like the gate. The source drain is self-aligned to the gate. These two pocket dope region are also self-aligned to the gate, just like source and drain. And the way it works is shown here. Yeah. So this is a schematic of the halo for this gate length. Okay. In the middle, there's almost no doping. Near the source drain is P+. Okay. But if the gate is shorter, okay, we do the same P+, but the middle will come up. Okay. Because of the P+ self-aligned to the source and drain. Okay. Now, this gate longer or shorter, this is not intentional. This is because of the technology tolerance. Okay, so let's say you want to print a 20 nanometer gate, but on a wafer, the gate can be a little longer than 20 nanometer or a little shorter. Sort of a statistical variation of gate length, even though design length is the same. But you end up with in the wafer, at some location, it's a little longer than 20 nanometer. In some location, it's a little shorter than 20 nanometer. In this case, the halo doping will help because if the gate is shorter, then those two P+, two halo region will be closer. The middle will go up, which means that this threshold voltage is higher than the upper case where the gate is longer. Okay. You see, the halo doping is self-aligned to the gate. So for longer gate, you have less halo doping with low doping in the middle. But if the gate is shorter, then the average doping will go up because the middle become highly doped. Okay, so in other words, halo what establish a trend that makes the VT go up when the gate is shorter, not intentionally, but due to the fabrication tolerance. So as a result of that, the VT tends to go up. In fact, some people call it reverse short channel effect. The short channel effect is the VT goes down when the gate is reduced, shortened. A reverse short channel effect is that the VT can go up, and that's due to this halo effect, because the doping was introduced after gate patterning. Okay, so the shorter gate will result in a higher sort of effective or average doping. So what's the benefit of that? Because that counteracts the short channel effect. Shorter channel effect means the VT goes down, the gate length becomes shorter. But the halo doping makes the VT go up because it makes the average or effective p-type doping of a shorter device higher than the longer device. Okay, so this means that to the first order, we can sort of cancel the short channel effect. So instead of VT roll off, okay, we use this effect for the for the VT to go up as channel lengths decrease to offset the short channel effect. Okay, so that's the reason for the halo doping. Okay, so the last part of chapter 6 is about the discrete doping fluctuations. Okay. Yeah, here's a Monte Carlo simulation of a MOSFET. Blue are the N plus source and drain, very highly doped, 10 to 20. The red are the p-type acceptor doping, it's the body or the substrate, and this is the this ideal low high and halo doping. But each point represents a doping atom. Okay. So the blue region, in this case, the channel length, I think it's 20 nanometer. Maybe shorter. Okay. But in any case, this granularity of doping atoms. Okay. The blue region are about 10 to 20 per cubic centimeter. Okay, so there's less granularity of doping atoms, but the channel region is doped something like 10 to the 19 or even 10 to the 18, so that you can see the granularity. And this is completely statistical, we cannot control where the dopant atom goes. We can only control the average dopant density. But in the actual hardware, this can fluctuate from device to device, okay, due to the discrete nature of dopant atoms shown here. Now we can have a very crude way of analyzing this effect. Okay, let's consider a MOSFET of width W, length L, and diffusion depth WD. And doping, let's say it's uniform, okay. Then the number of dopant atoms in this volume is W times L times WD times Na. So that's the number of dopant atoms in this diffusion region. That's the volume. That's the doping density per volume. Well, that's a number. But the actual number, you fluctuate by the square root of that. So the number is, if the number is n, then the fluctuation or the sigma mean square deviation is square root of n. Okay. And if there's a fluctuation of the actual number, then there's a fluctuation of VT because the diffusion charge in that particular device determines VT. Okay, if it's got a fluctuation, then VT has a fluctuation as well. So to the first order, we consider that this fluctuation due to the square root of the number translates into a diffusion charge per area of simply Q times this number, the square root number. Okay. And then the VT fluctuation is due to this diffusion charge fluctuation divided by the Cox total capacitance. Cox is per area times WL that's the gate area. So it's Cox or delta VT equal this. We put it together. But we do it more carefully. The diffusion charge effect on VT actually has a vertical depth dependence because the dopant atoms close to the diffusion region doesn't have much effect. The dopant charge close to the surface has a very strong effect on VT. Okay? So you end up with a sigma, this sigma of delta VT given by that. So if you look at some number, this is a 100 nanometer device with a length delta 18. That's the doping needed to control the short channel effect. And then we end up with the sigma is about 20 millivolts. Okay, for these numbers. Now 20 millivolt, it's not too bad. But when we consider a array of like a gigabit or even 10 gigabit, then we need a 6 sigma. So 6 sigma times 20 can be 100 millivolt, which means that in a large stacked RAM array, the VT, the worst case VT can be 100 millivolt, different from what your design value is. So this could be a problem. To the first order, if we use not the ground plane with undoped region of excess, that helps because, as I mentioned, the VT, the fluctuation, the VT fluctuation due to dopant atom is stronger when there's dopant vibration near the surface. But when the dopant changes the diffusion depth, essentially has zero effect. Okay, so in this case, it's greatly suppressed. But let's take that's the ideal case. But let's take a halo profile in the I call that. This is actually I call it super halo design. 25 this is a 25 nanometer. Okay. 25 nanometer. Okay, we take this and then we do a Monte Carlo simulation. Okay. This is 1D analysis. This is too crude. Okay. So we do that. Turns out the sigma to be 10 millivolt per micron, but it's proportional to square root of W. That comes from here. Now for a 25 nanometer, in principle, W equal to L. L is 25 nanometer. W is also 25 nanometer. Then, okay. So this is W in micron. Okay. If W is 20 nanometer, okay, that's 1 over 50 of a micron. Square root of that is 1 over 7, which means that the sigma VT is 7 times that if W is 20 nanometer. So if sigma is 70 millivolts, well, then we are in trouble because 6 sigma will be 6 times 70 millivolts. Now be 0.4 volts. Okay, so we cannot. So at a large SRAM, some cell will fail because of the the VT is either too low or too high. Okay, because for a large array, some device will have a VT deviation at the 6 sigma value, which can be as much as 4 tenths of a volt. If 4 tenths of a volt, the ideal VT is let's say 0.2, and with a 0.4 volt change or 0.2, then that cell may not work. So this is a key issue in terms of the state-of-the-art SRAM yield. Is because of this discrete dopant fluctuation. The problem is that there's not much we can do about it, because it's the atoms are discrete, whether we like it or not. Even though we model it as a continuum, but actually the atoms are discrete. So when device small enough, this kind of discreteness of nature of atomic discrete nature will show up. Okay, so that's the end of chapter 6. We have about 10 minutes left. So let's start on chapter 7. Okay. Chapter 7 is SOI, or silicon on insulator, CMOS. Okay. This is not in the mainstream of CMOS technology. Okay, most mainstream CMOS is bulk, but in some applications, people use SOI. More importantly, the well-known so-called FinFET, they are not bulk MOSFET, so they are in general a type of silicon on insulator. So we discussed that in this chapter. So first, I think we can talk maybe 3 charts here today. First, the structure looks like this. Instead of making the NMOS and PMOS, NMOS on the left, PMOS on the right, on the substrate, we make above substrate, we have a box called buried oxide, and then we have silicon islands, single crystal silicon for NMOS and PMOS. And it's all oxide below the NMOS and between the MOSFETs. The STI stands for shallow trench isolation, so that's oxide. So in this case, NMOS, PMOS are in separate silicon islands on top of a oxide layer, a thick called a buried oxide layer. The substrate is standard P-type or N-type, whatever you choose. Yeah. And so this type is called silicon on insulator, or SOI. Yeah. Just one chart on how people make SOI. The most successful company to sell SOI is called Soitec. This is a French company, SOITEC, and they developed a so-called Unibond process. What you do is you start with 2 wafers, A and B. You oxidize, and then you implant hydrogen, heavy dose, a lot of hydrogen implanted into one side of A. And then you bond the A and B, if you turn A around, okay, so the top becomes at the bottom, and the bottom is B, so it looks like that. This dashed is the where you did the hydrogen implant here. Okay. And the next step, you split. Split means mechanically you just try to peel the A off B. And because of hydrogen implant will weaken the silicon bond at this plane. So A wafer will split at that another plane, which leave a very thin layer of A over oxide, the reddest oxide that's grown here, and B. So B is the substrate. That's the buried oxide. And A is the silicon. The thin layer of silicon that we make device. And then, of course, you can oxidize the silicon to make the oxide isolation on top. Okay. And then you try to anneal and polish to clean up the damage. Okay. So we end up with so-called SOI. And the A can be reused. Okay, so in other words, it's not a two wafer, you end up with one, because that would increase the cost. You actually can use A over and over again. Okay. And so and this is called Unibond. Okay. So one more chart for today. This is general comparison between bulk, SOI, and I call it double gate. Okay. Bulk on the left, SOI in the middle, double gate on the right. The key difference is the doping or the scale length. Remember, in bulk, the bulk cannot be very lightly doped because we wanted the maximum diffusion width to be shallow enough to control short channel effect. Okay. Remember the lambda, the scale length factor. Okay. So when you make the channel length shorter, the diffusion width has to go down, which means that you have to raise the doping here. But for SOI, you don't need high doping because you have buried oxide underneath. Okay. So in this case, it's the oxide, it's the silicon thickness, physical thickness of silicon on top of the buried oxide that goes into the short channel effect. Okay. So for bulk, again, so bulk we need doping, but for here, it's the physical thickness of silicon. In particular, for double gate case, you have gate on both sides. This is FinFET. And FinFET is essentially a double gate. That goes sideways. We'll talk about FinFET fabrication later. But basically, it's a double gate. And so the silicon also has a certain thickness. So in this case, the physical thickness of silicon, P-silicon, will control the short channel effect. Okay, so the key point here is that the bulk, in the bulk case, it has to be doped to contain short channel effect. But for SOI and double gate, you don't have to dope the silicon to bring down the scale length of a MOSFET for short channel devices. But that's the key difference. Okay, so I think we'll stop today's class here, and we'll continue next Monday.